Part A says write the equation of the tangent line. Gives us a point. You know to find the slope. You take that point, you plug that into your derivative. So just use the x. So you get your e squared ln of e. We know ln of e is equal to 1. So your slope is e squared. There's your point. There's your slope. Do your point slope form. Boom. Get the equation of your tangent line. Part A is done. Part B was a little tricky. I actually like part C better than part B, but part B is a little trickier. Not too bad there, but it says it's the graph of f concave up or concave down. And so you know that means you're going to take the second derivative to look at that concavity stuff there, right? So do your product rule. I did first times derivative of the second plus the second times derivative of the first. Did a little bit of factoring. And then when I was trying to figure out whether this was concave up or concave, I'm trying to figure out whether this is positive or negative. So that determines whether the original graph is concave up or concave down. It said in between 1 and 3. So remember your ln of x graph, right? Looks like this. They crosses at 1. So in between 1 and 3, that ln of x is a positive number. It's above the x-axis. So if you take a positive number times it by 2, you still get a positive number. You add 1, it's still positive. And if your x is in between 1 and 3, that x right there is always positive there. So you just had to like think for a second, is this thing positive or is this thing negative? And then if you just know the basic shape of that graph and you're plugging in numbers in that interval, that second derivative, everything is positive there. And so since your second derivative is positive, that means your original function will be concave up. Letter C, anti-differentiation. That's the same thing as the integral, right? The antiderivative, the integral. And so you're going to call this dy dx, move the dx over, and then notice that the x's are already with the dx. If you have any y's over there, move them over with the dy, and then we're going to integrate both sides. And so when you integrate the one with respect to y, you're going to get y equals. And then look, you got a normal thing times a weirder thing. So I think we know that's integration by parts. And man, you better let the u equal that ln part of that problem, right? You have to let the u equal the ln part of the problem. Can't use a tabular method, can't use a shortcut on this one. Let your u equal the ln of x, your dv is the rest of it. Take your derivative, do your integral, and then your formula is u times v, write that down, minus the integral of v du. So when you multiply those together, I pulled out the 1/3, you get x cubed over x to get the x squared, integrate that, easy integral, and then when you get your y equals this, you gotta remember your plus c. They give us the point, that's our initial condition right there, there's our initial condition. So take the 2, plug it in for the y, take the e, plug it in for the x. You see all my work there, I ran out of room, so I go over here, and then I just had e cubed and e cubed, so I made that 3/9 minus 1/9 to get 2/9 e cubed plus c. Move that over. Your c, yeah, that looks a little funky, but we could handle that. I mean, this is the AP calculus test right there, so your c is equal to that weird looking stuff, and then just take that, plug that back in right there, insert that for the c, and then you have your original function. We like that problem. Lemonade.